This podcast was made specifically to discuss how metals, which have different oxidation states and ligands, can act very differently from each other. We have several important goals in this video. We're going to state how oxidation states affect a species' properties, state how these oxidation states can be changed, states how these cannot be changed, and relate these concepts to real-world applications, where understanding the difference in oxidation states and ligands is important to decision-making. Let's either learn or remind ourselves what an oxidation state is. You may have already covered oxidation states, but this podcast is meant to take a slightly different and more practical look at them. Oxidation states occur when a species gain or lose electrons to gain or lose a charge. Many metals have more than one of these states. One of the simplest ways that we can see a difference in the properties of oxidation states is to view the colors. They're not always different, but sometimes. Here is a nice summary infographic showing many of the different colors of a species. Vanadium, for instance, has 4 different oxidation states, and all of these happen to have very different colors when in solution. But that's really only the start of the differences. Atoms can change oxidation states when they react with other species that can be oxidized or reduced. For example, under the right conditions, sodium and chloride will react to form Na+ and Cl-, which will then form table salt. We'll learn more about redox reactions in other videos. For now, we'll just focus on the fact that they can be changed via special reactions. Sometimes this happens spontaneously, as with an apple turning brown, or a car rusting. And other times, it won't happen unless a very specific set of conditions are met, or unless energy is put into the system. For instance, with rechargeable batteries, the batteries will not undergo a recharge reaction unless they are first given electricity. Now at this point, you might say, so they are different colors. Are they actually that different? And yes, in many cases, the properties of different oxidation states are incredibly different. Let's take a look at one of the best known examples. Sodium. Sodium is extremely reactive in water. This picture occurs from throwing 1 pound of sodium into a lake. Many people have been injured by doing similar experiments, so please don't do this at home. Sodium is generally stored in oil to prevent it from reacting because it will even react with the air. This picture is a picture of that happening. Now let's compare that to Na+1. Most commonly known in daily life, this form is found in sodium chloride, or table salt. We know that adding table salt to water doesn't form a horrific reaction. Or I don't think that it would very much help a sore throat or allow the oceans to exist. And we know that our salt shakers don't spontaneously catch on fire in the air like this picture either. The two couldn't be more different. Different oxidation states have different properties and react with other species differently. Because sodium wants to become sodium 1+, it's violently reactive. But sodium 1+ is stable, and so it does not. And because it's stable, it also doesn't want to go back to sodium with no charge. So unless you put it under very specific circumstances, it's not going to do that on its own. Of course, when I say want, I'm anthropomorphizing. If you're in 1A, you'll learn more about what causes this in 1C. If you're in 1C, you'll learn about this when we talk about reduction potential values later in this chapter. And you'll see this when we get to tables like this. Now, let me throw out a hypothetical to you. A person says to you, you can't eat sodium because it reacts with water, so much so that it explodes. It is very dangerous. Take a moment and think about what you would tell this person. You might want to pause the video to give it some thought. Now, of course, you aren't going to stop eating sodium. First off, it would be nearly impossible as it's in almost everything. Secondly, your body needs sodium ions to survive. +1 ions to survive specifically. Even if you could stop eating sodium, you'd soon find yourself in dire need of it. The +1 in the 0 states of sodium react very differently to water because the +0 state wants to lose an electron, but the +1 state is stable. And you would need to find a way to explain that to the person depending on their level of understanding. Now let's switch gears from oxidation states to discussing how similar compounds can have very different effects. Though not a metal, I like this example due to the similarities in a later example that we'll look at. Ethanol is an alcohol that we can drink. Generally, we can drink a fair amount of this without death or any real significant long-term effects, assuming that you don't get into a car and crash it, or operate heavy machinery, or go home with someone you shouldn't, or the variety of things that it can cause you to do. Let's compare that to methanol. though in many ways it's incredibly similar to ethanol if we just look at the two. The small difference means that your body reacts very differently to it. Even drinking a very small amount of methanol can lead to blindness, kidney failure, or even death. Now let's look at another example, this time involving a metal. Aluminum is an incredibly common metal that's found in a variety of things. It's typically found as aluminum hydroxide or aluminum phosphate. We put these in deodorants and medicines such as antacids and vaccines. But it's found naturally in food like potatoes, spinach, and tea. In fact, a child that's of vaccination age gets more aluminum from their breast milk or formula than from anywhere else. It's incredibly safe. However, another form of aluminum, aluminum phosphide, causes death in extremely horrific ways. I decided not to put pictures of those in, as people get incredibly sick and eventually die of circulatory collapse, multi-organ failure. Our bodies just handle these two materials completely differently. So go ahead and eat your spinach and drink your tea and take your antacids, but be sure to skip the sprinkling of pesticides. My final example, and if we're being honest, the reason behind wanting to discuss these topics with you. To do this, we need to first consider some background information. Mercury vapor is quite dangerous. This can occur when a mercury thermometer breaks. Methyl mercury is a mercury that people are talking about when they discuss why pregnant people shouldn't eat fish, and why no one should really eat too many large ocean fish, which are known to accumulate this form of mercury. That's what they're talking about when they talk about bioaccumulation. Now, if you have read about ancient royals taking mercury pills and then going mad and dying, this was generally mercury chloride. It too is considered dangerous and caused a lot of really, really bad problems in people who took it as medicine. Now, let's talk about thimerosal. This was a preservative that was originally added to vaccines back before 2001. It was pulled due to public mistrust of the mercury compound, though it's been shown to be safe time and time again. The CDC and the FDA, along with other agencies, agreed to pull it from nearly all childhood vaccines, multi-dose flu shots being the main exception. And you can get single-dose flu shots that don't have that if you really want. It was pulled not for safety reasons, but to avoid people refusing to vaccinate their children due to fear because of it. Now, with all that background and the discussions that we've had so far, how would you respond to someone who says vaccines have mercury compounds in them, and therefore they are dangerous? Take a minute, review anything you need to review, and think about what you would tell them before listening to what I would tell them. There are lots of different ways to reassure someone about thimerosal. Of course, the biggest one is to remind people that there is no longer thimerosal in vaccines, not because it isn't safe, but because the FDA and the CDC were concerned about people's perception and chose to remove it to make sure that parents would continue to vaccinate their children. But if you want to talk about it scientifically, and you want to talk about both of the topics that we discussed in this video, it has a different oxidation state than many of the toxic forms of mercury, and it has different ligands from the other toxic forms. We can't infer toxicity based on the presence of an atom alone. Rather, we have to account for the entire molecule. Actual testing is the only way that we can know for sure what the exact properties of a molecule are going to be when introduced into the complex human body system.